3.5 is going to be on simplifying square roots and imaginary numbers. In the video notes part A, we're looking at simplifying square roots. Okay. So we already know that some numbers can look different but have the same value, such as 1.5, which can be 1 and 1/2. That's a different format for the same value. Perhaps 4/6, you can reduce that to 2/3. They have the same value, they look different. -10/2 is the same thing as -5, and 35% is the same thing as 0.35. Just examples of numbers that we already know come in more than one format. Now, with a few exceptions, there are some reasons that you might want to see one versus the other, where it might not matter which format you have. There are some where you really want to change one to the other because it is a reduced and simpler form in the middle two. That's going to be true of square roots as well. Okay, so we're going to find the following on our calculator just to compare them. So starting off here, let's see. The first one I have is the square root of 45. So I can see that's 6.708, and if I do 3 times the square root of 5, 6.708, they're the same decimal, so they have the same value. Both of those are approximately 6.708, etc. And if I look at the other two, it's another pair of values that are going to be the same. So if I do the square root of the fraction 3/8, or if I do the square root of 6, and then I divide it by 5, oops, that is not true that those are the same. So there is definitely, I don't know where those two came from, there's definitely some sort of mistake there. These are not the same, so that's just fun. I'll maybe update those to get to be the same someday. But they're not the same. Okay, so sometimes they're the same. We'll have to make sure we figure out when and when they're not by these rules that we're going to see here. First, I want to list the perfect squares. We'll talk about y in just a second right here. What are the perfect squares? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, I can't remember 14 squared. So if you can't remember any of these, you just square them and find out. 14 squared is 196. And then 225. So you want to be familiar with these numbers. So I have the first one grayed off because 1 goes into anything. We don't really care about 1 as a factor, so we're not going to think about 1 squared as 1. But we do want to think about the rest of these numbers, whether 4 or 9 or 16. Not the 2 squared, but the 4, the perfect square number. We want to be familiar with these perfect square numbers to see if they divide into something, so we'll know if they simplify or not. So when they simplify a radical, a square root is to be considered simplified if there are no perfect square factors inside the square root. That's the first one. There also need to be no fractions inside the square root and no square roots in the denominator. We'll get to those two parts later in class. However, the first one we're going to start with here, the no perfect square factors inside the root. So we're going to use the product property to separate radicals. So the product property says that if you have the square root of a times b, that's the same thing as the square root of a times the square root of b. Let's test that real quick with a few numbers. So for example, if I took the square root of 40 and I compared that with, I don't want to put a squiggle, I should put an equals because this is going to be actually equal right here. The square root of 5 times the square root of 8 to start with. Okay. So if I do the square root of 40, 6.32, etc., I can separate that into 2 square roots that multiply to 40, so 2 factors. So the square root of 5 times the square root of 8. They look the same. Okay. Now, in general, we don't want to pick any 2 numbers, and in fact, the 2 that I picked wouldn't be a pair that would be a good choice to break up. It's true that they're equal, but I want to work on perfect square factors. We're going to extra emphasize that perfect square factors. So I don't want to break that 40 down into just anything that goes into 40, like 5 and 8. But I want to know if one of these numbers goes into 40 because these numbers are perfect squares. and 4 goes into 40. So I'm going to write that up again up here. What if instead we did the square root of 4 times the square root of 10? Of course it's going to be the same decimal. Square root of 4 times the square root of 10, they have the same value. But the benefit of this one is now I can do the square root of 4, write it outside. The square root of 4 is 2. Leave the square root of 10 alone. So 2 times the square root of 10, it's all the exact same decimal value. But what we have right here is a radical that has been simplified, because the number inside the radical is smaller and that this number on the outside is not in a radical. We don't want 2 radicals, because 2 radicals is not better than 1 radical. But 1 radical with a smaller value in it is better than a radical, 1 radical with a larger number in it. Okay, so that's the goal. Just a little bit of insight into why we're doing this. Okay, so this little note down here, so step 1, we're looking at no perfect square factors inside the root. So we're going to break the radical down into a product of, noting that again, it needs to be a product of perfect square factors, not just any factors, but perfect square factors. Apply the product property and repeat as needed. So we'll try it with a few examples down here. 20. Okay, so if you're thinking to yourself, like making a list of things that go into 20, you might think, 20 is 2 times 10, but you don't care because 2 and 10 are on your list of perfect squares. That's not going to work. But 20 is 4 times 5, and since 4 is on your list, you're going to go with that pair. You're going to break this down because 4 is a perfect square. Only looking at perfect squares that divide into it. So if you grab your calculator and start trying to divide 20 by things to see what perfect square goes in, only divide it by these numbers, by your perfect squares. So I would start by writing that 20 is the square root of 4 times the square root of 5, and then I do the square root that I can do, the one that comes out evenly. So the square root of 4 is 2, then I have the square root of 5 left over. So my answer is 2 times the square root of 5. Okay. Trying the next couple. 54. I try dividing it by 4. It doesn't go in. I try dividing it by 9, and it does go in 6 times. So I'm going to write this one as the square root of 9 times the square root of 6. I do the square root of 9, so I get the square root of 9 is 3 times the square root of 6. I also always try to write the perfect square factor first, so that when I bring my numbers back down, the radical's naturally on the right-hand side. If you write them opposite first, you'll just switch on the next line, because you want your radical to end your statement and your whole number that comes out to be first. All right, and looking at the next one, I don't know 112, what goes into 112, so I'm going to try some stuff. It's even. I think 4 will go into it. Yeah, it does. So we're going to do 4 and 28 for 112. So I'll write that as the square root of 4 times the square root of 28. And I know that 4 is perfect, so I know that its square root is 2. So we have 2 times the square root of 28. Now, just to draw your attention back up here to the repeat as needed statement, this 28 isn't done because the perfect square 4 still goes into it. So I'm going to break that one down again. So that's 2 times, 28 is the square root of 4 times the square root of 7. Then I can do this again and say that this is 2 times 2 square root of 7, and 2 times 2 is 4, so it's 4 square root of 7. Okay. Now, I had to do it twice because I didn't choose the biggest perfect square first. I didn't know it went into 112, so I tried a little perfect square, 4, it did. But if I tried some of the bigger ones first, I might have found it a little faster. For example, if I took 112 and divided it by 16, which is a perfect square, I would see that 16 went in there 7 times. So if I went about that way, I'd have the square root of 16 times the square root of 7. I would know that the square root of 16 is 4, and then I had my square root of 7. I could have gotten that same thing right away in the usual 2 steps versus the 4 steps I had to take if I didn't happen to choose the largest perfect square. I can still get there using a smaller one first, but it is a little shorter if you pick the bigger perfect square the first time. So it's just something to look out for. Okay, and then 600. So again, 600 is 4 goes into it, but I want to go bigger. It ends in all those zeros. I know 100 goes into it, so I'm looking for a bigger perfect square. I know 4 and 25 both are smaller perfect squares that go into it, but if I can get that biggest, I'll save some steps. So we'll do that this time. So the square root of 100 times the square root of 6. The square root of 100 is 10. So I have 10 times the square root of 6. I know that I'm done because 6 does not have a perfect square that divides into it. You can't divide it evenly by 4 or 9 or any of these values. So 10 square root of 6 is our answer.